Hello everyone. Today I want to talk about the classical probability model. Um, Here is the outline of the talk. I'm going to talk about probability and then conditional probability. The third part is the total probability formula, and the last one will be the base formula. So I'm going to start with the first part, probability. As you may know, an experiment is a procedure that is carried out under controlled conditions, and it is executed to discover an unknown result. A trial is a single performance of an experiment, and an outcome is the result of a trial. Deterministic or predictable experiments and those which have only one possible result or outcome. In random experiments, there are different outcomes, even when repeated in the same manner every time. For example, when you flip a coin, you can get a head or a tail. When you roll a die, you can get any number from 1 to 6. Or if you roll 2 dice, you can get a lot of pairs. For example, 1, 1, 1 and 2, 1 and 3, and so on. Or when you measure the current, you may get many numbers, even when you repeat the same experiment. In order to proceed further, I want to define the sample space. So the sample space of an experiment is a set of all possible outcomes. For example, when you flip a coin, all the possible outcomes will be head or tail, so you get the set head tail. That would be the sample space. Or you roll a die, the sample space will be 1, 2, 3, 4, 5, 6. Or when you roll 2 dice, you can get 1, 1, 1, 2, 1, 3, and so on up to 6 and 6. There are two kinds of sample spaces. It could be discrete if it consists of a finite or countable infinite set of outcomes. If it contains an interval of real numbers, then you call it a continuous sample space. And all subsets of the sample space are called events. For example, consider the recycle time of a flash. You select a camera and record the recycle time of that flash. Then you come up with a set of all real numbers, and that set is called the sample space because the time has to be positive. It cannot be negative or 0. Now, suppose that all the recycle times are between 1.5 and 5 seconds, then the set 1.5 to 5 is continuous, and that is the sample space. Now, if you categorize the recycle time into 3 possible values, low, medium, or high, then the set low, medium, high is called the sample space of the experiment, and it is discrete because it contains only 3 elements. Now, if you consider whether the camera conforms to minimum recycle time specifications, then you come up with a set yes or no. And because it contains only 2 elements, that sample space is discrete. How about an event? An event A is a subset of the sample space of a random experiment. In reality, it could be a statement, a sentence, or a clause. For example, when you consider the recycle time of a flash, the set A1, which is the interval 1 to infinity, is an event. Another event is the set 1, 2. What does that mean? It means that the recycle time of a flash will be between 1 and 2 seconds. Or let's say A1. A1 is the event that the recycle time of the flash is at least 1 second. You can consider similar examples. I will skip them. And if you want to combine clauses, you need to use conjunctions, right? You can use and, you can use or but to combine clauses to make a statement. And in math, you need to use the operators to describe those conjunctions. So we are going to use a bar for not, a times b for and, a plus b for or, a minus b for but. A bar is the complement, and you can also denote it by AC or A prime. The product AB is in fact the intersection of A and B. And the sum of A and B is in fact the union of the two subsets A and B. For example, suppose that A is the event that you pass the course, this course, and B is the event that you pass the course of linear algebra. Then what is the complement of A? The complement of A is the event that you fail the course, you fail this course. And B bar is the event that you fail the course of linear algebra. How about the product of A and B? The product of A and B is the event that you pass both courses. And the sum A plus B is the event that you pass at least one of the two courses. Okay. And how about the difference? The difference A minus B is the event that you pass this course, but you fail the other course. Here are some rules that that may be useful for you, especially the Morgan's rule. A plus B, the complement of A plus B is in fact A bar times B bar. I'm going to explain it to you. So you see that right here we get the whole sample space like that. Okay, and I'm going to divide it into two parts. For this for B, and this for the complements, and I do the same thing for A bar and A. So you get A bar here. Okay, so this part will be A B, and this will be A B bar. All right, this cell is in fact the intersection of A bar and B, and this is going to be A bar and B bar. Okay. All right. We want to prove that the complement of A plus B is A bar times B bar. Okay. I hope that you can read my handwritings. Okay, so what is the left-hand side? The left-hand side is the complement of A plus B. This set is in A, and this set is in B. So A plus B is the combination of all the three cells. Okay, and the complement of A plus B should be A bar B bar, right? So that's why you have this equation. So this equation is correct. Okay. So you see that the first equation is valid. You can use similar arguments to verify the second equation. Now, what is probability? The probability is, in fact, the likelihood or chance that a particular outcome or event from a random experiment will occur. Roughly speaking, it is a number between 0 and 1. There are several kinds of probabilities. The first one is subjective probability. It is, in fact, the degree of belief, and it is derived from an individual's personal judgment or experiments. There are several kinds of probabilities. The first one should be subjective probability, which is a degree of belief, and it is derived from an individual's personal judgment or experience about whether a specific outcome is likely to occur. However, this probability is biased because it depends on the judgment of one person. Relative frequency probability is based on how often an event occurs over a very large sample space. For example, if you want to get the probability that you will get a head when you flip a coin, then you flip the coin like 1,000 times, and suppose that you get about 499 heads, then the probability that you get a head will be 499 over 1,000. How about the probability with equally likely outcomes? When you flip a coin, there are two possible outcomes. You may get a head or a tail. Therefore, the chance to get a head is 1 over 2, and the chance to get a tail is also 1 over 2. It seems right, but in reality, there are many cases in which we don't have that assumption. For example, you take this course and you can pass the course or you can fail the course. And obviously, we don't expect that the chance to pass the course is exactly 50%, right? So we will come up with the definition of modern probability with 3 axioms. So probability is a function from the collection of all events to the set of interval 0, 1, and you need it to be non-negative, and the set the sample space has probabilities 1, and if you have 2 disjoint events, then the probability of that sum will be the sum of the 2 probabilities. What does it mean by disjoint events? 2 events are disjoint if they cannot occur at the same time. For example, if A is the event that you pass the course and B is the event that you fail the course, then they are disjoint events because you cannot pass and fail the same course at the same time. For any event A, you call PA the probability of A. Properties of probability. Probabilities should be between 0 and 1, you knew that. And the probability of omega is 1. The probability of the empty set is 0, which means that the probability of certainty is 1, and the probability of impossibility is 0. However, the probability 0 does not mean impossible. What does that mean? I'm going to give you an example. We have an interval, like from 0 to 1, all right? And I'm going to pick a number denoted by x from that interval. Okay. And suppose that A1 is the event that the x is between 0 and 1/2. You know, the probability of the whole interval is 1, therefore the probability that x is in the interval 0, 1/2 should be at most 1/2, right? Okay. And how about A2? A2 is the event that x is between 0 and 1/3. What do you think about that? Well, we don't have the equal sign here. Okay. Then you get a similar result. This probability is at most 1/3. Okay. So in general, if you have the set AK, which is the events that x is between 0 and 1/k, then the probability that x is in this interval will be at most 1/k. Okay, so you see that in this inequality, the right hand side goes to 0. Therefore, the left hand side have to go to 0. And because the left hand side is also non-negative, and you see that this value is greater than the probability the probability that x equals 0, right? So from this you can conclude that the probability of A equals 0, right? The probability of A equals 0. And obviously, it is possible that you can pick number 0. Probability 0 does not mean impossible. Okay, it does if the sample space is discrete, but if the sample space is continuous, it's not true. Next, the probability of the column of A is 1 minus the probability of A. That is very obvious, so I will move to the next one. From the axiom, we knew that the probability of the sum A and B is the sum of the two probabilities A and B for two disjoint events. In general, if you have more than two disjoint events, A1 up to AN, then the probability of the sum A1, A2 up to AN is the sum of the probability of A1 plus the probability of A2 plus blah blah and the probability of AN. Let's consider the following example. If 3 fair coins are tossed, what is the probability that 3 faces will not be the same? This will be the events that you want to look at. So suppose that A is the event that 3 faces will not be the same. Then we had the word not, so you should think of the complement, and I want to find the probability of the complement A bar. What is the probability of A bar? A bar is the event that 3 faces are the same, and if they are the same, then you may get head 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 or tail tail tail. So there are two possible outcomes. You get 2 divided by 8, because if you don't care about the phases, then when you flip 3 coins, the number of possible outcomes should be 2 times 2 times 2, which is 8. Therefore, you get 1 over 4, this. And now you want to find the probability of A, which is 1 minus the probability of the complements. Then you get 1 minus 1/3. I'm sorry, 1/4 here. And you get 3 over 4. Next, birthday problem. You want to find the probability that in a set of 10 randomly chosen people, at least one pair of them will have the same birthday. Whenever you see the word not, or at least, or at most, you should think of the complement. In this case, you can use the complement of an event to solve the problem. Next, I want to talk about the addition rule. This equation looks quite similar to the one that we got from the axiom. However, we have one extra term. And the point is that we don't need the assumption that the two events are disjoint. For 3 events, you get the probability of A plus B plus C equals the probability of A plus the probability of B plus the probability of C. And then minus the probability of AB minus the probability of AC minus the probability of BC, and then plus the probability of ABC. Please note the alternating signs. So you have plus, and then minus, and then plus. I'm going to prove the first equation. The second equation is quite similar to that. That the probability of A plus B equals the probability of A plus the probability of B minus the probability of A, B. So I'm going to draw a diagram, the Venn diagram. This be A, this B, and this is going to be the intersection. Okay. So on the right hand side, you get the probability of A. So I'm going to count this part 1 time, this part 1 time, and add the probability of B. So I count this part 1 time, and the intersection 1 more time. Therefore, you need to subtract the intersection from the sum to get the probability of the union. Okay. In general, you can have a similar equation for more than 2 or 3 events, even though they are not disjoint. And obviously, if they are disjoint, then in the first equation, the last term will be 0. Therefore, you will come back to the equation you already knew. The same for the second equation. If they are disjoint A, B, and C, then the probability of AB, AC, BC, and ABC are 0. Okay. Now let's consider the following example of semiconductor wafer. The data are given in the table below. The wafers are classified by the contamination level and the location of the tool. There are 2 levels of contamination, low and high, and there are 2 locations of the tool, at the center or the edge. And as you may see that there are 514 wafers of low level of contamination at the center of the tool, 68 wafers of low level of contamination at the edge of the tool. Same for the other numbers. Now we select randomly a wafer from the batch and denote by H the event of high concentrations of contaminants. Then the probability of H is 358 over 940, and denoted by C the event of the wafer being located at the center of the tool. Then the probability of C will be 626 divided by 940. Now the probability of intersection HC is the probability that the wafer is of high level of contamination at the center of the tool. So you get 112 divided by 940. How about the probability of the sum H plus C? That would be the sum of all these numbers, 514, 112, and 246, all divided by 940. Well, now you can rewrite this sum, the sum of the numerator, in the following way. You get this one, okay? And you see that the first term is in fact the number 358, the probability of H, and the second term is 626 divided by 940 will be the probability of C, and then minus 112 over 940, which is the probability of the intersection. So you will see that the probability of the sum H plus C is the probability of H plus the probability of C minus the probability of HC. Let's consider the following example. A patient arrives at a doctor's office with a sore throat and low-grade fever. After an exam, the doctor decides that the patient has either a bacterial infection or a viral infection, or both. The doctor decides that there is a probability of 0.7 that the patient has a bacterial infection and a probability of 40% that the person has a viral infection. What is the probability that the patient has both infections? Let's solve this problem. Now suppose that B is the event that the patient has a bacterial infection, and V is the event that the patient has a viral infection. Then you want to find the probability that this person has a bacterial infection and a viral infection. Okay, and if you use the production the addition rule, you get the probability of B plus the probability of V minus the probability of B plus V. We knew that this probability is 0. Bacterial infection, it is 0.7. This is 0.4, and the last one will be 1 because the doctor said that the patient should have at least one infection. So after all, you get the answer 1.1 minus 1, so you get 0.1. Now I'm ready to introduce to you the next concept of conditional probability. What is this? The conditional probability of B given A is the probability of event B occurring given that event A has already occurred. For example, a communications channel has an error rate of 1 per 1000 bits transmitted. Errors are rare but do tend to occur in bursts. If a bit is in error, the probability that the next bit is also in error is greater than that. Another example. Suppose that A is the event that you pass the course, and B is the event that your GPA is high. Okay, so if I pick a student at random, then and based on the historical data, I get that a student passed the course is 70%. So if I have no idea about that person, then the probability of A, or the probability that the student passes the course, is 70%. But if I know the fact that the GPA of that student is high, then the probability that that student will pass the course is obviously greater than 70%. So we will come up with the following definition. The probability of A given B is the probability of AB divided by the probability of B. Why is that? Let's consider the following thing. This is the whole sample space. This is omega. And this is B. And this is B bar. Okay. And this is your A, the event that you consider. And you want to find the probability of A. So you know that this is in fact A over the whole sample space, omega. But if you know that B already occurred, if B already occurred, then B bar never occurs, right? B bar never occurs. So you can cross that part, and A becomes this smaller part, and it is AB. Okay. Therefore, the numerator will become AB, and the denominator will become B. That's why you get the probability of AB divided by the probability of B. Let's consider the following example. There are 4 scenarios when you check the surface of an item. You may see that there are some flaws on the surface or not, and that item could be defective or not. So in your experiments, there are 10 defective items with some surface flaws. There are 18 defective items without any flaws on the surface. There are 30 non-defective items with some flaws on the surface, and there are 342 non-defective items without any surface flaws. And 40, 360, 28, 372 are the marginal distributions. So in total, you have 400 items. Now, what is the probability of F? The probability of F is the probability that a randomly selected item has some flaws on the surface. And obviously, it is 40 over 400. Okay. How about the probability of D? The probability of D is the fraction 28 divided by 400. Now, you want to find, you know that the probability of D is 28 over 400. It means that if you select one item at random and you have no idea about that, then this is the probability that the item is defective. However, if you find some flaws on the surface, what do you think? If you find some flaws on the surface, then you may think it might be defective, right? So this is what you want to find, you want to check. And how can you get that? There are two ways to get the answer. This is the first way. By the definition, it is in fact the probability of the F, the intersection, divided by the probability of F. And the probability of DF is 10 over 400 divided by the probability of F, so you get 40 over 400, and if you simplify the fraction, you get 10 over 40. Now, what is the probability of D given F? The probability of D given F is the probability that the item is defective if there are some flaws on the surface. So you only focus on this column, right? Because you already knew that there are some flaws on the surface. So F already occurred and F prime cannot occur. Then you only focus on this, and this becomes the size of the sample space. Therefore, you get immediately 10 over 40. Okay. You may see that the two numbers are the same. So why don't we use the second approach? Well, obviously the second approach is faster, simpler, but it means that you have to change the sample space every time you compute it. If you use the definition, you don't have to change the sample space. And in general, it will be better. Now, let's consider the following example. This data show confirmed cases of COVID-19 in Japan. And you see that in the first column, the age bracket, you get 0, means the age of the patients is between 0 and 10, and then same for the others. And the second columns are for male, then female, and then the total numbers. Okay, now suppose that a patient is randomly selected. Then what is the probability that the patient is male? So you see that it should be 456 divided by 843. Okay. So that is the probability of F. Now, what is the probability that the patient is male, given the fact that the age is between 10 and 20? Then we only focus on the second row, and you can say that the corresponding probability is 4 over 7, not 456 divided by 843 any longer. Now consider another example. Roll 2 dice and observe the numbers coming up. And suppose that A is the event that the sum is 6 and B is the event that the numbers are not equal. Find and compare the probability of B and the conditional probability of B given A. The probability of A is when you roll 2 dice, so sum is 6 means that you get 1 and 5, 5 and 1, 2 and 4, 4 and 2, 3 and 3. So this becomes 5 over 36, right? Okay. And how about the probability of B? The probability of B is the probability that the numbers are not equal. Not equal. Therefore, you want to think of the complement. And this is the second term is the probability that they are the same. And that would be 1 minus, if they are the same, then you get 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, 6 and 6. So you get 6 over 36. Probability of B given A. That would be the probability of AB or BA divided by the probability of A. What is the numerator? The probability of B given A is the probability that the sum is 6 and the numbers are not equal. So you get 1 and 1 and 5, 5 and 1, 2, 4, 4, 2, but not 3 and 3. So you get 4 over 36. While the denominator is 5 over 36. We already knew that, okay, over here. So you simplify this fraction to get 4 over 5, okay. Obviously, this value is not the same as, oh, I'm sorry, this is going to be 6 here. So they are not exactly the same, not exactly the same. Okay. Now, it is the event that the number showing on the first line is even, and F is the event that the sum is 7. So the probability of F is the denominator will be 36, right? The sum is 7, so you get 1 and 6, 6 and 1, 2, 4, 2, 2, 5, 5, 2, 3, 4, 4, 3. So you get 6 over 36. So that would be 1 over 6. And how about the probability of F given E? It is the probability of Fe divided by the probability of E. The probability of Fe is the event that the sum is 7 and the first is even. So you get 2 and 5, 4 and 3, 6 and 1. So you get 3 options over 36 divided by the probability of E, which is the probability that the first die is even. So you get 1/2, right? You simplify this fraction to get 1 over 6. Now you compare these two numbers, you see that they are exactly the same. Okay. Later you see that the two conditional probabilities and unconditional probabilities could be the same or different. If they are the same, you say that the two events are independent. Otherwise, you say that they are not independent. A and B are independent or stochastically independent if the conditional probability and the unconditional probability are the same, which means that knowing B occurred doesn't impact whether A occurred. The following statements are equivalent. A and B are independent if and only if the conditional probability of A given B is the same as the unconditional probability of A, or the conditional probability of B given A is the same as the unconditional probability of B, and the probability of A times B is the same as the probability of A times the probability of B. You have to remember that if A and B are not independent, then the probability of A times B is not the same as the probability of A times the probability of B. I want to talk about the case of Sally Clark. Sally Clark is a solicitor in the UK. She was the victim of a miscarriage of justice when she was found guilty in 1999 for the murder of her baby. The first baby, Christopher, died after 11 weeks in 1996, and the second son, named Harry, died after 8 weeks. And then she was convicted in November 1999. The first appeal was dismissed in fall 2000. However, after the second appeal in 2003, she was released, but she was found dead in her home in 2007 due to alcohol poisoning. What happened to her? In this case, Sir Roy Meadow was a professor and doctor in the UK. He was a British pediatrician at the St. James University Hospital. So obviously, he was a very famous person, and he was an expert witness in cases of suspected child abuse and murder. So in the case of Sally Clark, Sir Roy Meadow testified that the frequency of SIDS in an influenced family, non-smoking families, is about 1/8500. And the chance of 2 children from that family suffering SIDS was 1/8500 squared, which means 1/73 millions, which is a very small number, right? So that's why they conclude that Sally Clark was guilty and put her to jail. However, in 2001, the Royal Statistical Society in the UK issued a press release that summed up the 2 major flaws in his arguments. He added 2 major flaws. He argued that the probability of A1, A2 is the same as the probability of A1 times the probability of A2, where A1 is the event that the first child died, and A2 is the event that the second baby died. However, it is not true. Why? Because there is strong evidence that the SIDS does have genetic or environmental factors that may correlate within a family. And people found that the probability that the second death given the first death should be 1/77 instead of 1/73 millions. Now, there is another flaw. The probability of murder given the evidence is not exactly the same. Is not exactly the same as the probability of evidence given the murder, right? So, what you want to compute is the left-hand side, and what you can compute is the right-hand side. For example, suppose that a DNA sequence occurs in 1 in 10,000 people. Does this mean that if a suspect DNA matches that found at a crime scene, the probability that he is guilty is 1/1000, 10,000? That is not true. Now suppose that the city has 1 million people. then the DNA gives the odds of 100 over 1 against the suspect being guilty. Now, let's talk about the independence of 3 events. We already knew the independence of 2 events. If you have 3 events, then and each pair of them are independent, then we say that they are pairwise independent. It means that when you compute the conditional probability A, B given A, B given C, C given B, C given A given C, you can drop the condition. However, if you have 3 events involved in this probability, for example, the probability of A given BC, then you cannot drop the condition. If you want to do that, then you need the assumption that they are mutually independent. So 3 events are mutually independent or just independent if they are pairwise independent, and the probability of A, B, C is the same as the probability of A times the probability of B times the probability of C. Or you can say that you can always draw the conditions of the events when you compute the probability of the other events, like A given B is the probability of A given C is the probability of A, B given C is the probability of B, the probability of A given BC is the probability of A. Now, I want to give you another example. A batch of 50 parts contains 10 made by 201 and 40 made by 202. We select 2 parts randomly. What is the probability that the first part came from 201 and the second part came from 202? In the example, you have to find the probability of the intersection instead of the sum. So we need to use kind of the product rule instead of the addition rule. Now, denoted by E1, the events that the first part came from 201, and E2 is the events that the second part came from 202, then the probability of E1 is in fact 10 over 50 because there are 10 parts made by 201, and in all there are 50 parts. So you get this probability. Now, if the first part came from 201, then what is the probability that the second part came from 202? After you select the first part, then there are only 49 parts left, and 40 of them are made by 202. Therefore, the probability of E2 given E1 is 40 over 49. Then the probability of the intersection is 10 over 50 times 40 over 49. And then you simplify the fraction to get 8 over 49. And so in general, you have the following equation. The probability of AB equals the probability of A times the probability of B given A. You can also write this equation in the following form because AB and BA are the same. So you get the probability of BA and then the probability of B times the probability of A given B. Now, we already knew the product rule. The probability of A, B is the same as the probability of A times the probability of B if A and B are independent. In general, if you have many independent events, then the probability of the product is the product of the probability of the events. We are going to use that equation to solve the following example. Assume that the probability that a wafer contains a large particle of contamination is 1%, and that the wafers are independent if 15 wafers are analyzed. What is the probability that no large particles are found? Suppose that E1 is the event that the first wafer contains no large particle. E2 is the event that the second wafer contains no large particle, and so on. Then you want to find the probability of E1 times E2 times E15. And that would be the probability of E1 times the probability of E2 times the probability of E15 And then you come up with 0.99 times 0.99 and so on. So you get 0.99 to the 15 and you get 0.86. What if A and B are not independent? If A and B are not independent, then you can use the definition of the conditional probability to get the following equation. The probability of AB is the probability of A times the probability of B given A, and the probability of B times the probability of A given B. And obviously, if A and B are dependent, then the second factor will become the unconditional probability, and you get back to the original equation. In general, if you have three events, then the probability of A, B, C is the probability of A times the probability of B given A times the probability of C given AB. In general, if you have more than three events, then you can come up with a similar equation like this. Consider the following example. The probability that a part made in the first stage of a machining operation meets specifications is 90%. And suppose that the probability that it meets specifications in the second stage, given that met specifications in the first stage, is 95%. What is the probability that both stages meet specifications? Well, suppose that A is the event that the part has met the first stage specifications and B is for the second stage. Then you want to find the probability of A and B. And you come up with the probability of B given A times the probability of A using the product rule. And the first one is 95%, the second factor is 90%, then you get the answer. Let's try question 22. Celine is undecided as to whether to take a French course or a chemistry course. She estimates that her probability of receiving an A grade will be 1/2 in a French course and 2/3 in a chemistry course. If she decides to base her decision on the flip of a fair coin, what is the probability that she gets an A in chemistry? Now, we have two cases. She chooses French course or she can enroll in a chemistry course. In this course, the chance for her to get an A is 1/2, and this is going to be 1/2, and in chemistry course it should be 2/3, and then 1/3. So get an A or not, get an A or not. Okay. So you want to find the probability that she get an A in chemistry. Get an A in chemistry is the one. And the chance for her to take a French course is 1/2 and 1/2 for chemistry course because she based her decision on the flip of fair coin. Then this will be the probability of C times the probability of A given C. And the first factor is 1/2. That's valid. The second factor is 2/3. 2/3. So it should be 1/3. I will talk about the total probability formula. I will start my talk with an example. Here is the example. Celine is undecided as to whether to take a French course or a chemistry course. She estimates that her probability of receiving an A grade will be 1/2 in a French course and 2/3 in a chemistry course. If Celine decides to base her decision on the flip of a fair coin, what is the probability that she gets an A? I'm going to draw the corresponding probability tree. There are two scenarios. She can take a French course. I will denote the event by F. and she can take a chemistry course. That event is C. In its course, she can get an A or not. Then I will denote by A the event that she gets an A, and A bar is the event that she cannot get an A. The probability that she takes a French course is 1/2, and the same for another course. In a French course, the chance that she gets an A is 1/2, and in a chemistry course, that chance is 2/3. Now we want to find the probability that she gets an A. So I will focus on these events and this one. Okay. And how can you come up with these events? You have to follow this scenario or this scenario. So the probability that the first scenario occurs is 1/2 times 1/2. The probability that the second scenario occurs is 1/2 times 2/3. So you get 1/4 for the first and 1/3 for the second. To sum up, you can see that the probability that she gets an A will be 1/4 plus 1/3. You see that the probability of A is in fact 1/2 times 1/2 plus 2/3 times 1/2. And then you get the probability of A given F times the probability of F plus the probability of A given C times the probability of C. This equation is called the total probability formula. Here is the theorem. The probability of A equals the probability of A given B times the probability of B plus the probability of A given B bar, the complement of B, times the probability of B bar. We can prove this equation very easily. The probability of A is the probability of AB plus the probability of AB bar. Because the union of AB and AB bar will give you A, and that is joint, so you can use the addition rule to get this equation. On the other hand, the first term on the right hand side, the probability of AB is the probability of A given B times the probability of B due to the products rule. And the same for the second term, the probability of A B bar is the probability of A given B bar times the probability of B bar. The same for the second term. The probability of A B bar is the probability of A given B bar times the probability of B bar. Let's consider another example. Information about product failure based on chip manufacturing process contamination is given below. Find the probability of failure. There are two levels of contamination, high or not high. If the level is high, then the probability of failure is 10%. Otherwise, the probability of failure is 0.5%. The corresponding probability of each level is 20% for high level of contamination and 80% for not high level of contamination. Now we want to find the probability of failure, and there are two scenarios again. So denote by F the events that the product fails, and H the events that the chip is exposed to high contamination during manufacture. Then the probability of failure is the probability of FH plus the probability of FH prime or H bar. And the first term is the product of the conditional probability of F given H times the probability of H. So you get 0.1 times 0.2, which give you 0.02. The second term, the probability of f h prime, will be the probability of f given h prime times the probability of h prime, which is 0.05 times 0.8, and then you get 0.04. In all, you get 0.024. Next, let's consider the following example. There are two boxes. Box 1 has 3 green and 2 red balls. Box 2 has 4 green and 6 red balls. You withdraw a ball at random from box 1 and transfer that ball to box 2. Then select another ball from box 2. What is the probability that the ball drawn from box 2 is green? I'm going to draw the tree. Suppose that G1 is the event that the first chosen ball is green, and R1 is the event that the first chosen ball is red. And then G2 is the event that the second chosen ball is green, otherwise it is red. And then G2 and R2. Now, at the beginning, in box 1, you have 3 green and 2 red. In box 2, there are 4 green balls and 6 red balls. Now, the probability of G2 should be the probability of G2 given G1 times the probability of G1 plus the probability of G2 given R1 times the probability of R1. The probability of G1 is the probability that you get a green ball from box 1 at the first time, and it should be 3 over 5 because there are 5 balls in box 1 and 3 of them are green. So it is 3 over 5. The probability of R1 is 2 over 5. Now, what is the probability of G2 given G1? It is the probability that you get a green ball from box 2 if the first chosen ball is green. So if you select one green ball from box 1 and you move it to box 2, then in box 2 there are 11 balls and 5 of them are green, not 4. Therefore, this value is 5 over 11. And this is 4 over 11. If the first chosen ball is red, then in box 2, there are 11 balls and only 4 of them are green. So you see that in this tree, you get 3 over 5, right? And then you get 5 over 11. And this is 2 over 5. And you have 4 over 11. You plug everything into this expression to get 5 over 11 times 3 over 5 plus 4 over 11 times 2 over 5. And hope that you can do the math to get the answer. Now, what if there are more than 2 events? Then the answer is yes, you can generalize the total probability formula. But you have to remember that all the events BI are disjoint, and the union of those BI should be the whole sample space. Let's consider the following example. We continued the discussion of contamination during chip manufacture, and you want to find the probability of failure. In this example, there are 3 levels of contamination: high, medium, and low. The corresponding probability of failure are 0.1, 0.01, 0.001. How can we do that? So again, suppose that F is the event that the chosen chip fails, H is the event that the chip is exposed to high level of contamination, M is the event that a chip is exposed to medium level, and L is the event that the chip is exposed to low level. So you see that the probability of H is 20%, the probability of M is 30%, the probability of L is 50%. And if the level is high, then the probability of failure is 0.1. If the level is medium, then the probability of failure is 0.01. And if the level of contamination is low, then the probability of failure is 0.01. And then after all, you get 0.0235. Another example. A bin contains 3 different types of disposable flashlights. The probability that a type 1 flashlight will give over 100 hours of use is 70%, with the corresponding probabilities for type 2 and type 3 flashlights being 40% and 30% respectively. Suppose that 20% of the flashlights in the bin are of type 1, 30% are of type 2, and 50% are of type 3. What is the probability that a randomly chosen flashlight will give more than 100 hours of use? So I will denote by T1 the events that the chosen flashlight is of type 1, and then I have T2 here, and then I get T3. The corresponding probability will be 20% for the first, 30% for the second, and 50% for the last one. Suppose that A is the event that the chosen flashlight will give more than 100 hours of use, then the probability of A in the case that T1 occurs should be 70%. And if it is of times 2 flashlight, then you get 40%. And then you get 30%. And we only focus on the probability of A, so you get 0.2 times 0.7 for the first case, 0.3 times 0.4 for the second, 0.5 times 0.3 for the last one, and the sum of everything will give you the answer, 0.41. So 41% is the probability that a randomly chosen flashlight will give more than 100 hours of use. I'm glad to introduce to you the base formula, the last part of this chapter. It is easy to prove the formula. The probability of AB is equal to the probability of A given B times the probability of B. It is the product rule. The probability of B times A is the probability of B given A times the probability of A. And because AB and BA are the same, we can conclude that the right-hand side of the two equations are the same, and you get the conditional probability of B given A times the probability of A is the same as the conditional probability of A given B times the probability of B. And we can divide both sides of this equation by the probability of A to get the probability of B given A equals the probability of A given B times the probability of B divided by the probability of A. What is the meaning of this equation? You can see that on the left-hand side, we get the conditional probability of B given A, while on the right-hand side, we get the conditional probability of A given B. So whenever you want to switch the two events in a conditional probability, you should think of the Bayes formula. Now we can combine this equation and the total probability formula to get the Bayes formula. We have these two equations, and the second equation is the total probability formula. We can plug the second equation into the denominator of the first equation to get the Bayes formula. And it is useful to notice that the numerator of the fraction on the right-hand side is always one of the terms in the denominator. In this case, the numerator is the first term in the denominator. I'm going to use the Bayes formula to solve the following example. In answering a question on a multiple choice test, a student may know the answer or not, and the probability that the student knows the answer is 80%. Suppose that a student who doesn't know the answer will be correct with probability 25%. What is the conditional probability that a student knew the answer to a question given that he or she answered it correctly? I'm going to draw the probability tree to describe the problem. Okay, I will denote by K the events that the student knew the answer to the question, and C is the events that the student answered the question correctly. And I will denote by G the events that the student does not know the answer. So we have two cases. He may know the answer or not, and he can answer the question correctly or incorrectly. The probability that the student knows the answer is 80%. The probability that he doesn't know the answer is 20%. If he doesn't know the answer, the probability that he gets the answer correctly is 25%. And the probability that he answered the question correctly, if he knows the answer, is obviously 100%. Now, you want to find the conditional probability of K given C. The probability that he actually knows the answer given the fact that he answered the question correctly. So this is the probability of C given K times the probability of K divided by the probability of C given K times the probability of K plus the probability of C given G times the probability of G. The probability of K is 0.8, of G is 20%, C given K is 1, C given G is 0.25. And for the numerator, it is exactly the first term of the denominator. So you get 1 and 0.8. Okay, so you can do the math to get the required probability. Let's do another example. A lab blood test is 95% effective in detecting a certain disease when it is in fact present. However, the test also uses a false positive result for 1% of the healthy people tested. If 0.5% of the population actually has the disease, what is the probability that a person has the disease given that the test result is positive? So I'm going to denote by D the events that the person has the disease, and plus is the events that the test is positive. So we want to find the probability of D given plus, and that would be the probability of plus given D times the probability of D divided by the probability of plus given D times the probability of D plus the probability of plus given H, where H is the event that the person is healthy, times the probability of H. So if you draw the diagram, you get D and H, and you get 0.5%, so it should be 0.005 and 0.995 for this. And if has the disease, the probability that you get a positive result is 95%, so 0.95. And if the person is healthy, then it is 1%, 0.01. Therefore, you come up with the following fraction. For the denominator, you get 0.95 times 0.005 plus 0.01 times 0.995. And for the numerator, you get 0.95 times 0.005. And you can simplify this fraction to get what you want. For the previous version of the base formula, you get 2 terms in the denominator. Can we have more than 2 terms? The answer is yes. If you have more than 2 events, let's say you have B1, B2, B3, then you may have more than 2 terms in the denominator of the base formula. Let's try question 32. Identify the source of a defective item. Suppose that there are 3 machines, M1, M2, and M3. The probability that the first machine produces a defective item is 1%. The corresponding probabilities for the second and the third machines are 2.5% and 2% respectively. The percentage of items made that come from each machine is 50%, 30%, and 20% respectively. Now, suppose that we select an item and it turns out to be defective. Which machine do you think that it should be the source of the item? Then I'm going to compute the probability of M1 given D, the probability of M2 given D, and the probability of M3 given D. And I will compare them. For the first term, I get the probability of D given M1 times the probability of M1 divided by the probability of D. And that would be, for D given M1, you get 0.01 times 0.5 divided by the probability of D. So you get 0.005. And for the second, you get D given M2 times M2. And that would be 0.025 times 0.3 divided by the probability of D. And you get 0.0075. And for the last one, you get the probability of D given M3 times the probability of M3 divided by the probability of D. And then you get 0.02 times 0.2 divided by the probability of D. And you get 0.004 divided by the probability of D. Now, because these three fractions have the same denominator, we only need to compare the numerators. And because the second fraction has the greatest numerator, we can conclude that the probability of M2 given D is greater than the others. And it is likely that the second machine is the source of the defective item. Question 33 is quite similar to those that we have done so far, so I will leave it to you. We can try to solve the problem at home. Thanks for watching.